Okay, so welcome guys. So in this video, we are trying to introduce the main subroutine of Shor's algorithm. So just as I previously said, the resulting state will be, let's say, r r plus r plus s r plus 2s up to r plus l1 minus 1 l minus 1s, and then take the square root of l. And so the idea is that we need to extract the information of S. Okay, so there's a thing called a Kroner Fourier transform, and we will introduce in the other videos. So basically, there's a FQ such that the FQ ij component will be omega ij, take a square root of Q, and omega is Q roots, so Q roots of unity. So the idea is that although it's Q by Q, but actually there's a polyglot Q qubits such that you can implement this quantum Fourier transform. Okay, so I take some example like F2, F4. So yeah. Okay, so the important is just this part. Okay, so this part is our main results. Oh, it's a little bit large. Okay, so we apply the let's say if we apply our quantum Fourier transform on the original phi, we get us 1 over square root QL, k from 0 to q minus 1, l from 0 to l minus 1, omega r plus l s k. Okay, and then we measure k. Okay, so there's the strange thing is that for each k, right? For each k, the coefficient is this. So small l equals 0, go to l minus 1, and omega ksl. Okay, so there's a dual simplification that s divides q. Okay, so if s divides q, then okay, so by the way, this guy is this guy, right? And one can rewrite it as omega ks to the power l from 0 to l minus 1. So it's the geometric series, and the answer will be it. So if omega ks is non-zero, then you will see there will be a phase difference. So there will be oscillated a lot. So generally, then it will be close to 0. If we further assume that S divides Q, then it will definitely be 0. Okay, so you can check this. But you see, if Ks, right, if this Ks is amazingly a multiple of Q, then the 1 plus omega Ks up to 1 plus L1, L minus 1 Ks will be 1 plus 1 plus 1 plus 1, go to L. So this is a very amazing result that if Q is a multiple of Ks, Ks is a multiple of Q, basically Q divides Ks, then all of these terms will add up to L. Okay, so this tells you that in general, if you have large probability to get K such that this integer K times S will be multiple of Q. So that means that K can be written as CQ divided by S. C is some integer. So we have K divided by Q equals to C divided by S. Then also one measure K, and we already know Q, right? Because Q is 2 to the n. Okay, so we get K over Q divided close to this C over S. So the idea is that we need to get S. Okay, so there's a technique called the continuum fraction to find S. So for example, if you measure K over Q, you get 0.25001. Then you can use a continuum fraction to guess that K divided by Q will be 1 over 4. Okay, so the final result is that we can use this Shor's algorithm to find S. So once we find S, then we have suppose we got two conditions. The first one is that if S is even, and the second one is that if x to the s divided by 2 minus 1, or x divided s divided by 2 plus 1 is not multiple of n, then that means one can just compute a GCD of x to the power s divided by 2 minus 1 n, and GCD x s divided by 2 plus 1 n to get P and Q. Hence, one can just break R as A. Okay. So there are a lot of mathematical analysis that show that for a large probability, even though that even though in usual case that S will not exactly divide by Q, S will not exactly divide Q, then one can still show that this term will be close to zero. So, or you can have the error bound. Okay, and the continuous fraction is also easy to be the error bound, but this is the general structure of the content of the Shor's algorithm. So the basic idea is that the Shor's algorithms can solve this period finding and find such as. Okay, so this is very amazing because I think there's some number theory which involves to solving this problem. So this means that quantum computing can have some impact to this abelian group, basically this number theory results. Okay, and I think so this is the important subroutine of the Shor's algorithm. So I think it's enough for I just introduce Shor's algorithm up to this level, and the next time we can talk about a complexity complexity implication from Shor's algorithm. Okay, so I will see you guys in the next videos.